Okay, let's get started with the Module 6 Learning Guide. So we're just going to go through this. It's actually a relatively short section, and some of it we've already covered. The first thing they do is introduce polynomials, but we've already done that earlier in a previous module, so just remember that polynomials are just the functions where the formula looks like regular numbers times variables, and the only powers you're allowed to have of variables are whole numbers that are positive. So right here it says the one right here on the left, the exponents must be non-negative integers. That's true. The coefficients of the variables must be non-negative integers. That's false. You could think of a quick example, something like f of x equals negative 5x squared minus 2. That would have two negative coefficients, but it's still a polynomial. The thing to worry about is the exponents. The graph of a polynomial may have a gap or break. That is false. So the graphs of polynomials are always continuous. And some of these things we've seen before with examples doing quadratic functions and so on. Those are always parabolas, or other ones we've looked at. So the next thing, it talks about the leading coefficient test. And so let's look at a few things there. Basically, the leading coefficient test basically says that's all you have to do is look at the biggest power and the number in front. So if you have some polynomial, basically it's going to have one number that is the biggest power, so here n is the largest exponent. And all the other stuff is just other terms. Because what the leading coefficient test is telling us is, as we get really big, what's going to happen with our arrows. So there's four things that can happen. So one simple scenario is eventually both sides will go up. So I think your book says both sides rise. Scenario 2 is you have something else where both sides end up falling. And then you have the scenario where you have one side rising and the other side falling. So here we might have some behavior where we fall to the left and rise to the right. And we also have the kind of symmetric version where we rise to the left and fall to the right. And basically we can determine which one of these four things is going to happen by looking at the pictures. So in picture 1, this happens when A is positive and n is even. Scenario 2 happens when A is negative and n is even. Scenario 3, again, this one is A is positive and n is odd. And the last one, A is negative and n is odd. Okay, so this is what happens in general. So we can kind of just look at a polynomial and determine the stuff by looking at the biggest coefficient. So let me give you some more concrete examples so you kind of know what I'm talking about. So kind of really basic versions of these would be f of x equals x squared. You have the graph just behaving like this. F of x equals negative x squared looks like this. F of x equals x to the third power looks like this. Then you have f of x to the negative x to the third power looks like this. So notice this is exactly the kind of situation we looked at above. In this case, f of x equals x squared. We have a is 1. You don't see a number in front, but when they don't write a number, that just means 1 is really there, and n is equal to 2. In this one, we have a is equal to negative 1, n is equal to 2. This one we have a is equal to 1, n is equal to 3. And then this one we have a is equal to negative 1, and n is equal to 3. So in a little bit, when we start looking at the in-between behavior, we will know exactly what happens in the middle. So this is just kind of telling us what happens at the end. So if we have something like f of x equals 17x squared minus x to the fourth, I'm not exactly sure what happens in the middle yet. I will be in a little bit. But here I know that a is equal to negative 1 and n is equal to 4. So eventually both sides should go down. So some funny stuff may happen in the middle, but eventually both sides of the graph are going to have to go down. It may even look like this, but eventually both sides go down. And the only thing to keep in mind is notice the leading term doesn't always necessarily come first. It's always we're looking for the biggest power. So in this case, that's the 4. All right, so that's basically the leading coefficient test in a nutshell. Just remember there's 4 scenarios. Look for n being even or odd, and then a being positive or negative. And you can remember the rule, but really what I do is if I know the pictures of these 4 graphs really well, then I understand the leading coefficient test intuitively. Okay, so that's the screen recording software. I meant to click OneNote and go back to the learning guide. Okay, so leading coefficient test to determine the end behavior of each function. We just need to figure out what n is and what a is. So in this case, n is equal to 3. 5x to the third is the leading term. A is equal to 5. So this means the picture will roughly do this eventually. So we can say the left will fall and the right side will rise. And that's how they do it on MyMathLab as well. On one like this, we have complete factored form. So what would the leading term be? Well, we have 3 factors, and you just pick the biggest x value from each factor and then multiply them together, and that'll be your leading term. So here it would be negative x squared times x, which would give negative x to the fourth. So from the leading coefficient test, we know that this actually, both sides fall. Because our polynomial has a equals to 1 and n equals to 4. Excuse me, a is equal to negative 1. That's what I meant to say. Also notice one other interesting thing. We know what's going on at the zeros here. There's 3 zeros. X equals 0, x equals 1, and x equals negative 3 are the 3 x-intercepts. So when you draw this graph, since both sides fall, we actually know there's something going on at x equals 1, x equals negative 3, and x equals 0. And so 1, negative 3. We know outside these points, both sides have to fall. And I can tell you that this graph actually will look like this, roughly. How do I know it looks like that? Well, there's a little trick that tells you exactly how the graph behaves at each of the zeros. It's called the multiplicity. And the multiplicity is the power of each factor. So keep clicking the wrong thing. So to determine intermediate behavior, we write in complete factored form. So we've had lots of practice with factoring, so that should not be an issue. And the second thing we do is we look at the multiplicity of each zero. So this is code for power of the factor. And there's two things that can happen. If the multiplicity is even, the graph bounces off. And if the multiplicity is odd, it passes through. So let me make up a quick example for you. Let's say we want to sketch a graph of f of x equals x to the third times x minus 2 to the fifth times x plus 3 squared. Okay, so first of all, we have to determine what is the degree of the function. So the leading coefficient test, we know n is equal to, well, we'd have an x to the third, an x to the fifth would come from the second factor, and an x to the second would come from the third. So 3 plus 5 plus 2, when you multiply that out, would give you 10. And then we know here a, the biggest one, is just going to be 1 again, is 1. So we know both sides will rise eventually. Then we have 3 x-intercepts. X equals 0 from the first one. X equals 2 from the second one. And x equals minus 3 from the third one. So our quick graph will have 3 places where it hits the x-axis. 0, 2, and minus 3. And what's going to happen at each one of them? At x equals 0, that's odd power, so it's going to pass through. X equals 2, it's odd, so it's also going to pass through there. And then x equals minus 3, it's even, so it's going to bounce. And we know from the leading coefficient test that both sides rise. So we've got arrows rising, and then we just have to figure out what happens at each one. So at negative 3, I bounce off. And then at the other ones, I pass through. And that is my behavior. So that would be a pretty quick sketch of the graph of f of x. Okay. Number 4, they want you to find all zeros. So this is just practice factoring. So this one we're going to factor by grouping. So this is just a review, but let's do it just for practice. So we're going to group the first pair and then group the second pair. So the first pair we can take out an x squared and we get x plus 2. And the second pair we'll just take out negative 1 and we'll have x plus 2 there. Then each term, the two terms, have the common factor of x plus 2. So we have x squared minus 1 times x plus 2. And then there's one more thing to factor. This first factor, x squared minus 1, is a difference of squares. So that means we can write it as x minus 1, x plus 1, x plus 2. Okay. Looking at number 5, find the zeros of this and get the multiplicity of each zero, and then state whether it touches or turns. So I say bounces for instead of touch, and they say turns and that's instead of passing through. But here we only have two zeros. X equals 3, corresponding to the first factor, with a multiplicity of 1. Since there's no factor, really this means there's a 1 there. And then x equals minus 6, and that has a multiplicity of 3. So if you actually wanted to get a graph of this, what's going to happen is you just figure out what happens. So also we need to say what happens, but at each one it's going to pass through. So we have 3 and we also have negative 6. So here's this. Then let's figure out the end behavior. So we have a 4x to the first power and x to the third power. That's 4x to the fourth power, so both sides should end up rising. So it just passes through, maybe some funny stuff happens, but eventually we're just going to get something like this. And that is how we graph number 5. Okay, the intermediate value theorem is pretty nice. Let me give you a quick idea about what that means. So this is a nice theorem. So for any polynomial, so this is the intermediate value theorem. I'm going to say for any polynomial, but this actually works for any continuous function. If f of x is less than 0 for some value, and we'll say some x equals a, and f of x is greater than 0 for some x equal to b, then for some value between a and b, f of x will equal 0. Okay, so I always think about this theorem pictorially because it's telling you something about the y values. So if you have a function, and let's say we have, well, a should be over here and b should be over here. So let's say at a it's below 0 and b it's above 0. Well, if a function's continuous, which all polynomials are, then you have to be able to connect these by moving from point A to point B without lifting your pencil off the paper, which means at some point in between we're going to get a value equal to 0. So this is really what's called an existence theorem. So there exists a 0 for the function, which is a nice thing. It's only so great, though, because it doesn't tell you how to find it. It just tells you there is at least one. There might even be more than one. For example, the function might do something really crazy. It, might go through a bunch of times and then stop there. But it tells you, if we have this value at one endpoint, and we know how to have that value at another endpoint, then somewhere in between we're going to have to cross the x-axis. So this is the existence theorem, the intermediate value theorem. So for a polynomial, if you can show that one x value gives a y that's less than 0, and another x value gives a y that's bigger than 0, then there must be some value that makes the y value equal to 0. So that's what they're talking about here. So they want to show that the function has a real 0 between -1 and 0. So we just plug in each one. So f of -1 will equal 2 times -1 to the fourth minus 4 times -1 squared plus 1. So this is equal to 2. That's going to be positive 1 minus 4 times 1 plus 1. So we end up with 2 minus 4 plus 1, which is minus 1. So this is less than 0. And then we also have f of 0. That's just going to be 2 times 0 to the fourth minus 4 times 0 squared plus 1, which equals 1, which is bigger than 0. So by the intermediate value theorem, so by the IVT, for some x between x equals minus 1 and x equals 0, there is some x such that f of x equals 0. This turning point thing is also another pattern that's interesting, so I will talk about that briefly. So turning points. So if f of x is a polynomial of degree n, it can have at most n minus 1 turning points. And turning points, again, remember these are maxes or mins, or pictorially, graphically, tops of hills, or bottoms of valleys. So this doesn't say it has exactly n minus 1 turning points, just, it can have that many. So there are some degree 3 graphs that might look like this. So this would probably be a degree 3 polynomial with 1, 2 turning points. This would be something like f of x equals x plus 2 times x minus 2. That graph would look like this one. But if we look at the simpler function, f of x equals x to the third power, that goes straight up. So it doesn't stop and actually turn. It's increasing across its entire domain. So this one has 2 turning points. This one has 0 turning points. So let's go back to the learning guide. And they say if f is a polynomial of degree 4, what is the greatest number of turning points? And we would just say it can have at most 3 turning points. All right. So they talk about the 5-step strategy. That's just everything we've learned so far. We just look at factoring first. Well, they determine n behavior, which we could do it in either order. If we want to do n behavior first, notice a equals 1, n equals 4, so we know that both sides go up. Or both sides rise. Step 2, we want to factor this. So x to the 4th minus 9x squared. They have a common factor of x squared. Then we have x squared minus 9, which factors as a difference of squares. X minus 3, x plus 3. Okay, so then we see that there are 3 zeros. X equals 0, x equals 3, and x equals minus 3. At this 0, it will bounce because it's multiplicity 2. At this 0, it will pass through because it's multiplicity 1. And at this one, it will also pass through because it's multiplicity 1. So if we want to do a quick and dirty sketch of the graph, we have 0, we have 3, and we have minus 3. And we know it's bouncing off this middle 0, and eventually both sides go up. So then we just have to connect them, and there's only one right way to do it, really. So we pass through this one, we bounce off the middle one, and then we pass back through the last one. And that's our graph, kind of like an upward W. Okay, so let's start talking about dividing polynomials. So 3.3 focuses on polynomials and long division. So this is going to operate a lot like long division arithmetic from grade school or high school. So what I recommend here is they say divide this number by this one. And we're always going to be looking for degrees, but notice there's some missing in between. 4 is the highest, and when we divide, what we should do is we should always try to remember to write down all of them. So there is no x to the third power, so what I'm going to do is I'm going to add a plus 0x to the third. And then I have minus 4x squared. And I have plus 6x. And then there's no constant term, so I can also do plus 0 there. And I just want to do that so that things line up better. You'll see what I mean in a minute. So now the key to polynomial long division is we always just want to look at putting the leading term of the polynomial we're dividing into the leading one here. So basically we have to ask ourselves is what number times x gives me 4x to the fourth power? So that's 4x to the third power. And then what we do is we multiply that times x minus 4. So x times 4x to the third is 4x to the fourth. Now we take x third and multiply it by 4. So we get minus 4x to the third. So what I did there really is I just took 4x to the third times x minus 4, and I multiplied by each one. And that's how I got this right here. So now we take that and we subtract it from the things above it. So 4x to the fourth minus 4x to the fourth is 0. And now we're subtracting negative 4x to the third, so we get positive 4x to the third. And we bring down the next term, minus 4x squared. Now we play the same game again. We ask ourselves how many times will x go into 4x to the third. Now it's just 4x squared times, and we multiply back through. So we're going to get 4x to the third, and now when we multiply 4x squared times minus 4, we'll get I multiplied wrong when I did it the first time. Can you believe that? Gosh, so sorry. Let's start over. I messed up at the beginning. At least I caught my mistake. Okay, so the problem is right here. Sorry, I still need to erase the other thing. Okay, so when we multiply 4x to the third, we get 4x to the fourth here, but the second term, 4x to the third times 4, should give me minus 16x to the third. And that's what we have to subtract. Okay, so now when we subtract the 4x to the fourths, we'll cancel, and we'll just get positive 16x to the third. Then we bring down the minus 4x squared. Now we go to the next step. So, what will that be? Well, 16x squared multiplied by x gives me 16x cubed. So up here I write 16x squared. 16x to the third is the first term. And what is 16 times negative 4? That should be minus 64x squared. Okay, now I subtract these. So the 16s cancel. If you did it right, the first term always cancels, and you'll have one left over. So now we have minus 4x squared, and then the two negatives will make this plus 64x squared. So that'll give me 64x squared minus 4x squared, which is 60x squared. Then we bring down the next one, 6x. Okay, so we have to do plus 60x. So 60x times x gives me 60x squared. 60x times minus 4 is minus 240x. Now I subtract this. So this will give me plus 240x plus 6 will be 246x. And then I just have plus 0. So only one more to bring down. Sorry, I went way too far into the end of the document. Okay. So really we just need to put 246. So we're going to have plus 246. And then after that we'll have a remainder, because we'll have 246x and then plus 246 times 4 is like, let me see, I think that's 4 times 250 would be 1,000 minus 4. Let's just do a calculator. I think it'll be like 984, but I'm not sure. So 246 times 4, yeah, 984, so I'm still okay. I hope I didn't make some sort of sign error through here, but that'll give me minus 984, and everything else will cancel, and that'll be your remainder, positive 984. So that's your remainder. So I want to check the answer just before we move on, because it's possible I made a mistake. Nope, 984 is the remainder, so we're good. Okay, so what does that mean? That means that when you take 4x to the 4th minus 4x squared plus 6x over x minus 4, this really equals 4x to the 3rd plus 16x squared plus 60x plus 246 plus the remainder is just the same number over the divisor, 984 over x minus 4. So they didn't give us a lot of room on that one. But that's what it means. Same way they did it over here. If you compare it to the other one, they divide this number by the divisor to get the quotient. So the number inside the house divided by the number outside the house gives the number on top, plus the remainder. The remainder is what they had at the very last step over the initial divisor. That's what we have. So this number over this number gives you the number on top. Okay. Here they use the synthetic division method, but I don't know. You don't really need to use synthetic division if you don't want to. You can just use regular old long division, which is my preference. I don't think it's necessary to go through the method. I think regular old long division is just fine. So let's do the same process. So x plus 5, how many times does x go into 3x squared? 3x. 3x times x will give me 3x squared plus 15x. And I subtract. So I get 7x minus 15x gives me minus 8x minus 20. And then how many times does x go into minus 8x? Minus 8 times. So minus 8 times x is minus 8x. Minus 8 times 5 is minus 40. And then when we subtract, that minus 40 will turn into a plus 40. So the 8's will cancel. We'll end up with just positive 20. So this will be remainder 20. So in this case, it'll be 3x squared plus 7x minus 20 over x plus 5 equals 3x minus 8, and then plus that remainder over x plus 5. Alright, so let's see if we got that one right too. Just like to check. 3x minus 8 plus 20 over 5. Synthetic division is just this trick where you just add the numbers. So rather than write the number on the outside, x plus 2, you write the 0 it corresponds to, negative 2. And then you take all the other coefficients from this one. So notice it's x cubed 1 plus 0x squared minus 7x minus 6. And then you just start multiplying. So 2 times negative 1. We bring down the 1, multiply by negative 2, add it to the top, multiply it, add them up, multiply it, add them up, and you see what you get. So it's literally the same exact procedure, but a little more clandestine. So I just prefer to use the long division when I do it. If you like synthetic division, go right ahead, but long division is the same thing. So I generally won't be requiring too much that makes use of the synthetic division, but when you do, you can still just always use the long division is what I would recommend. So alright, so now let's talk about the remainder theorem. So the idea of the remainder theorem is just that if you have f of x equals, let's say, x plus 5 times some complicated stuff, x squared plus 36x plus 22 plus 34, something like that. Then if we do f of minus 5, what's happening? Well, we're going to get 0 times something plus 34. Well, 0 times something just makes that all go away, and we just get the 34 that's left over. So if you take your polynomial and you divide it by x plus 5, then you're just going to end up with a remainder when you plug the 0 value in. So I know that's kind of a quick explanation, but that's what they mean here. So they're saying use the remainder theorem to find f of 4. So basically our step 1 would be divide 2x to the third minus 11x squared plus 7x minus 5 by x minus 4. Why x minus 4? Because x minus 4 corresponds to the 0 x equals 4, which is what we're plugging in. So let's do the division in the notes so we have some a little bit of extra space. So 2 minus 11, 7 minus 5. So we want to do I might be messing up the powers. Yeah, I'm all off by 1. Sorry. Alright, so 2, 11, 7, 5. Minus plus minus. And what were we dividing by? X minus 4, because x equals 4 is the 0. So how does this work? Well, 2x squared multiply 2x to the third minus 8x squared. And we subtract. We get minus 3x squared. Bring down the 7x. So we need minus 3x. Multiply, we get minus 3x squared plus 12x. Subtract, minus 5x. We bring down the minus 5. Okay. So now that goes in minus 5 times, and we get minus 5x plus 20. And then when we subtract this, well, the 5's will cancel because it'll be minus 5x plus 5x, and minus 5 minus 20 will be minus 25. So our remainder is 25, negative 25. So what does that mean? Well, it means our problem, maybe I have some room over here, means that we can write the big thing, minus 2x cubed minus 11x squared plus 7x minus 5. This is really equal to x minus 4 times the 2x squared minus 3x minus 5 plus the remainder of negative 25. So when you plug in x equals 4, this whole part will be 0 and go away, and we'll just end up with minus 25. So f of 4 will be minus 25 is our answer to the problem back on the learning guide. So then we plug in 4. So basically for us, we saw that f of 4 equals minus 25. Okay, so let's go down and double check. Hey, look, it's minus 25. All right, one more. Another similar kind of equation. They say, solve the equation given that this is a 0. Well, that means we want to divide. Remember, 0, if they say 2 is a 0, that corresponds to the factor x minus 2. So basically, divide by x minus 2 and see what's left over. Okay, so 2x cubed minus 5x squared plus x plus 2. So another division problem. 2x cubed minus 5x squared, and I can't remember for the life of me, plus x plus 2. And we want to divide that by, I think, x minus 2. Right? Just double check that. I think they said 2 is a 0, so x minus 2 would be the factor. They say 2 is a 0, so x minus 2 is the factor. Yeah, just like we said. Okay, so let's get back to division. So we do 2x squared on top. We multiply, we'll have 2x cubed minus 4x squared. And then we subtract. So this will give us minus 5x squared plus 4x squared, which is minus x squared. Bring down the x. That'll go in minus x times x is minus x squared. Minus x times minus 2 is plus 2x. Then we subtract. So we'll get minus x. Bring down the 2. That will go in exactly one time, minus one time, and the remainder will be 0 because we get minus x plus 2. And when we subtract that, that's the same exact thing. So it equals 0. So this tells us that we actually have a factorization. So 2x cubed minus 5x squared plus x plus 2 is really just equal to x minus 2 times 2x squared minus x minus 1. So to find all the zeros, let's see if we can factor that anymore. So does 2x squared minus x minus 1 factor? Let's see, 2 times negative 1, negative 2. Are there factors of negative 2 that add up to negative 1? There sure are. So if you double check 2x and x, if we put a minus 1 here and a plus 1 here, and you FOIL it out to check, we'll see that we get 2x squared minus 2x from the outside plus x from the inside, gives me minus x in the middle, and then minus 1 at the end. So this really factors into 3 terms, x minus 2, 2x plus 1, and x minus 1. What are the zeros of each one? That has the 0, 2. This one has the 0, negative 1/2. This one has the 0, positive 1. Notice if you plug in 2 for x, you get 0 here. Plug in minus 1/2. Here you get 0. And plug in 1 there, you get 0. So that will be the solution to our solution set for our learning guide. So solution set is 2 minus 1/2, and the last one was just 1, I think. Yep. Is that what they got? 2, 1, and minus 1/2. Sure did. Okay, the last section really just talks about the rational roots theorem. So I know it's been a pretty long time, but the way that we do the rational roots theorem is not that hard. It's a little tedious, but this will be basically the only type of question you'll see from the last 3.4 section. So the rational roots theorem tells us all possible rational roots. It doesn't tell us that there are any, but it tells us if there are any, they have to come from a certain classification of numbers. So we look at roots of the bottom, or roots of the constant term over coefficient roots of the first term. So the possible factors of the constant term in this case 6 has a few, plus or minus 1 is the smallest. Then it could also be divided by plus or minus 2, plus or minus 3, or plus or minus 6. Those are all the numbers that divide positive 6 evenly. And then factors of the leading term. This one there's actually not that many because 3 is prime, so it's just plus or minus 1 or plus or minus 3. So to figure out all the possible factors, what we have to do is we have to make all possible fractions with factors from the constant term on top and factors from the leading term on the bottom. So possible zeros. And they'll ask these questions on MyMathLab. They're not that bad though. So plus or minus 1, so we look at 1 over 1. Then we look at 1 over 3, so we also have plus or minus 1/3. Then we have 2 over 1, so plus or minus 2. And we have 2 over 3, so plus or minus 2/3. Then we have 3 over 1, so that's plus or minus 3. We have 3 over 3, which is plus or minus 1, but we already have that written down, so we don't need to write it again. Then we have 6 over 1, so that's plus or minus 6. And then 6 over 3 is plus or minus 2, which we already have written down, so we don't need to write again. So you basically go through and have to look at all the possible factors of the constant term, all the possible factors of the leading term, and then you take the zeros by putting all the possibilities where the constant's on top and the leading is on the bottom. So if you put them in order, it would go 1/3, 2/3, 1, 2, 3, and 6. So again, let's just check to make sure we did that right. Yeah, so 1/3, 2/3, 1, 2, 3, and 6. So yeah, we sure got it. And then, so these are all the possible zeros, but how big is the f of x? It's actually, it's actually only degree 4. So we know only 4 numbers can make it 0. So the best way is you actually just have to go through and test them all. So you plug each one in and see. This one, technically, they didn't tell us to find the zeros, so we're good with just listing them all. But on this next one, they actually want us to find all the zeros. So let's go ahead and start with the same thing. So we have factors of the constant. That's 6 in this case, or negative 6. So we got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then we have the factors of the leading, which in this case is actually only plus or minus 1. So when you make fractions, it's actually exactly the same because plus or minus 1 on the bottom only leads to the same numbers as the factors of the constant term. Okay, so those are all the possible zeros. And now that's all we do to do it is you can either go through and use synthetic division, or what I do is I just plug them into the function. So test them out. So test one by one. So if you have 1 and you want to see if it's a 0, you just plug 1 in and you see what happens. So that's 1 to the 3rd power plus 4 times 1 squared minus 3 minus 6. So that gives me 1 plus 4, so we get 5 minus 9, which is minus 4. So that one's not a 0. Let's test negative 1. So you get negative 1 to the 3rd power plus 4 times negative 1 squared minus 3 times minus 1, minus 6. So this gives me negative 1 plus 4 plus 3 minus 6. Hey, guess what? This equals 0. So I know negative 1 is a 0 of the function. All right, now that I have one that's a 0, I can go ahead and do polynomial division. So let's divide x to the third plus 4x squared minus 3x minus 6 by x plus 1. That's the factor that corresponds to negative 1 as a 0. So let's do that here. So we want to divide by x plus 1. And then I think we have x to the third, trying to remember, 4x squared minus 3x minus 6. And then this should divide evenly since it was a 0, so it goes in x squared times x to the third plus x squared. We subtract them off, get 3x squared, bring the next one down, minus 3x. So here what are we going to do? We're going to do plus 3x, get 3x squared plus 3x, and then when we subtract, get minus 6x, bring down the minus 6, so then we get minus 6, and then we get minus 6x minus 6, so the remainder is 0. Okay, so that tells me that x to the third plus 4x squared minus 3x minus 6 is really equal to x plus 1 times x squared minus 3x minus 6. And the second one factors into x. This one might not factor, so we might have to actually use a oh, it's plus 3x, plus 3x. Does that make a difference? I don't believe it does. I'm just trying to see if it factors. You would need factors of minus 6. So it's either minus 6 and positive 1, which will be 5 or negative 5, or negative 3 and 2, which will be plus or minus 1. Yeah, so to get the other two zeros, we're actually going to have to do a quadratic formula here. So to find zeros, of this factor, we use the quadratic formula. With A equal to 1, B equal to 3, and C equal to minus 6. So let's do that quickly. So here we'll have x is equal to negative b plus or minus the square root of 3 squared minus 4 times 1 times minus 6 all over 2 times 1. So this will be equal to negative 3 plus or minus the square root of 9 plus 24 over 2. So this is negative 3 plus or minus the square root of 33 over 2. So those are our other two zeros. So not super nice, but we can still find them. So notice those are both rational zeros, or irrational zeros, so those don't even appear in our possible list. So our solution set ends up being negative 1, negative 3, plus the square root of 33 over 2, and negative 3 minus the square root of 33 over 2. And that's a very typical style of problem where we're using the rational roots theorem. So let's go to the bottom and see if we actually got this one right. Yeah, we sure did. Negative 1, negative 3 minus the square root of 33, and negative 3 plus the square root of 33. So those are basically the last ones. Some of these, like they have complex roots. So number 4, we're actually going to stop here. Number 4 doesn't apply to us because we're not doing any complex algebra. We're sticking with the real valued stuff for the most part. And some of this stuff, basically, you would solve number 3 the same way we solved number 2. You'd look at possible rational roots, which just come from the divisors of 12, because the leading coefficient is just plus or minus 1, and then you go through and test them all. It can be kind of tedious, but that's it. So on the test, you'll basically only see 1 or 2 of these. There's also a handful of problems on Descartes' law of signs on the homework. If you get stuck there, just send me an email. We're not going to do any examples of those, but if you just click view an example, it'll tell you the rule. And basically, it's just talking about how many zeros you're going to have of each type when the sign changes between each term. So according to Descartes' law of signs, this changes 1 from plus to minus, and then that's it. So that'll basically tell you how many possible zeros to have according to some formula. I have 1 or 2 of those on the homework, but definitely won't be on the test. So that was kind of a long lecture, but thanks for sticking with me, and I hope you learned something. If anything's not clear, just send me an email and we can talk through it, or schedule a meeting in my office hours. Okay,